Hi, my name is James Johns. I'm an assistant professor of chemistry at the University of Minnesota, and I'm putting together a YouTube video series on how to build an electronic structure program. I recently taught quantum mechanics and spectroscopy to our undergraduates, and I realized there is a big difference between what we can cover in a class for undergraduates and sort of where the starting point is for how one would actually do an electronic structure calculation. So while teaching that class, I wrote a simple Hartree Fock program in Matlab to show to some of the students. And in this video, we're going to go over how to build your own simple Hartree Fock program. Now, there are two main goals for doing this. The first is to better understand what happens in an actual electronic structure calculation, especially when you're doing with a molecule that's more complex than, say, H2+. The second is to give a general idea or a feeling for how we can program some of these calculations. It's easy to go to a book and look up what the formulae are, and sometimes it's not obvious, especially if you're a chemist and you've never seen programming before, how to actually implement them in a program. So in this program, in this video series, we're going to learn how to program a simple restricted Hartree Fock program in Matlab. And I chose to do this in Matlab because many universities have free access to Matlab for students. It's also very easy to implement numerical functions in Matlab. It's not the fastest program ever. We're not writing this for speed, we're writing this for clarity. So everything that we're going to do here is pretty much just a direct implementation of the formula that you might find in a book on electronic structure calculations or electronic structure theory. Now this does turn out to be a relatively decent amount of code. I think it's a couple thousand, it's about 1,000, 1,500 lines worth of code. And so if you haven't done much programming before, this might give you an idea of how we're going to use things like functions and arrays and structures and control loops in order to make the calculation really go or to drive it. Okay, at least that's the hope. So why do we need to use computers for this anyways? It turns out we can write down the Hamiltonian for a molecule relatively straightforwardly. There's nothing mysterious going on there. We know what all of the interactions are. The problem is that the electron-electron repulsion term makes it really difficult to solve for the eigenvalues of the Hamiltonian in any realistic pen and paper type of sense. So what we do is we simplify the problem. We simplify it in two ways. The first is we make the Hartree-Fock approximation, which is rather than dealing with the full electron-electron repulsion, for each electron, we say that it feels an average or a mean field electron repulsion energy due to the presence of the other electrons. This means that we lose correlation information, so one electron can't effectively avoid another if it's moving around the average potential. And so we lose a little bit of energy or correctness there. That can be accounted for later. The other thing that we do is, rather than trying to integrate the Schrodinger equation and get the exact solution, we're going to solve the Schrodinger equation, or the molecular Hamiltonian, using a finite basis set. And this basis set is going to consist of Gaussian functions, maybe they're multiplied by polynomials that are centered on each atom. And these Gaussian combinations of these Gaussian functions are going to be what we use to create our actual individual independent electron orbitals. Okay. And because we're solving this in a finite basis set, what that means is we're going to evaluate a number of operators and construct them explicitly in our basis set. So if we use 20 basis functions, then each of our operators is going to be a 20 by 20 matrix, where each matrix element, O sub mn, is going to be the integral over all space of basis m times operator O acting on basis n. Okay? We're going to be primarily concerned with the operators that show up in our Hamiltonian, and our Hamiltonian can be split up into 4 basic operators. The first is the nuclear repulsion energy. This doesn't depend on the electrons at all. We're going to assume that the nuclei are fixed in space, which is basically the Born-Oppenheimer approximation. And so that's a very simple sum. If we tell the program where the nuclei are and what the atomic number of each nuclei is, we can calculate that very quickly. Then there are the one electron operators. It's going to be the kinetic energy of the electrons and the electron nuclear attraction energy. These are relatively straightforward to solve, to evaluate those matrix elements. And the last one, the real kicker, is the electron-electron repulsion matrix. And in order to calculate that, we're going to build a sort of a helper matrix, which is going to be a 4-dimensional array. It's going to be number of bases times number of bases times number of bases times number of bases. And then we're going to select elements of that to create our actual electron-electron repulsion. And that's sort of what we're going to do. As you might be able to get the feel for, this is going to involve a substantial amount of code, and so we're going to do things in 3 steps. The first step is we're going to write a program that can calculate the different matrix elements that we're going to need, and we're going to restrict ourselves to using only s orbitals. The reason for using s orbitals is that the math and the programming is just simpler. We don't have to worry about the angular momentum components. And we get all the basic physics there anyways. Once we have our matrix elements, we're going to write another program or routine that's going to take those matrix elements, the total number of electrons and our basis functions, and it's going to do the self-consistent field method to find the lowest energy states, and then we're going to populate those 2 electrons per orbital. Okay. We'll add those up to get our final total energy. Now, it turns out that once we build that program doesn't care about angular momentum. All the angular momentum information is in the matrix elements. And so once we built that subroutine and can calculate things for s orbitals, we'll expand the program and look at the matrix element program to include different angular momentum values. Okay. So the general structure for the actual program is that we're going to break this up into a variety of smaller programs. We're not going to try and write this all in one giant document where Matlab goes through and does each function one by one by one. Instead, we're going to have one big master program, which we're going to call Hartree Fock driver, and that's going to drive the program. And the only thing we're going to give that is our atomic numbers, the locations of the nuclei, and then we're going to use a specific basis set, which will depend, the details of which will depend on the atomic numbers. That big driver program is going to call in itself smaller programs, which we'll store in separate files, and those smaller programs will be what calculate the matrix elements. And then in order to calculate the matrix elements, we're going to need to know how to perform those integrals, and we're going to have another set of very small programs that do very specific things that we're going to use over and over again within the different matrix element builders. Okay. All right. And so for our HF driver, we're going to go ahead and build that now. And then the next couple of videos, we'll build the programs that help us build our basis sets and then calculate the actual matrix elements. So for HF driver, the only things we need are a list of the atomic numbers. So if I have a methane, I would need to give it that we have 1 carbon and 4 hydrogen atoms. So that might be a list that's 4, 1, 1, 1, 1. And then I need to tell it what the coordinates of each of the individual nuclei are. And so it's going to be a n, where n is the total number of atoms, by 3 array. Okay. And then once we get that, we're going to just declare a number of functions that we're going to call later. And so our HF driver program is going to need to build a set of basis functions based on the nuclei that we give it. From the nuclei we give it, it needs to calculate the nuclear repulsion energy. And then we need to start dealing with the electrons. So given our basis set, they are Gaussian functions. They're not actually going to be orthonormal. And so we need to calculate how much each basis function overlaps with every other basis function. we'll then calculate our one electron operator. So we'll calculate the kinetic energy matrix for the basis set, and then we'll calculate the nuclear attraction energy, which is how much each electron in each basis function would be attracted to each of the nuclei. Okay. And then we'll do the hard part, really, which is building the electron-electron repulsion matrix. And then once we have all of that, we'll feed that into another program, which will do the self-consistent field method and return one number, and that number will be the final energy. And so now I'm going to hop over into Matlab. I'm going to open up Matlab, and we're going to start to build this. So to open it, we're going to type in edit HF driver, which will open the folder, or open the file hfdriver.m. And then in here, we're going to start building our program. So this is going to be a function that returns a minimum energy equals HF driver. And we're going to have to give it our list of atomic numbers and our atomic coordinates. Okay. Once we give it that, then we're going to start building each of those individual subroutines. So let's actually make a little comment here. HF rise the HF calculation for a user supplied vector, type here vector of atomic numbers, and M, we'll use M as the total number of atoms for a reason they'll become apparent in a second, M by 3 array of atomic coordinates. Okay? Alright, and so once we have those, then we can start implementing our function. So we can actually, just from the atomic number and the coordinates, we can go ahead and say nuclear, we can build our nuclear repulsion. Build nuclear repulsion. And that's going to be a function that takes in the atomic number and the atomic coordinates. And then the next function that we're going to need is we need to build our basis set. And so we're going to say, by putting this in brackets, we're going to have it return multiple values. And we're going to have a function that says build basis. And it's also going to take in our atomic numbers and coordinates. And it will return a cell structure of basis functions, and we'll define what that is, and the total number of electrons in our system. Once we have that, we can start building our matrices that we're going to need to calculate our total energy. So we're going to say S equal build overlap. S is the common letter used for an overlap matrix, and all we need to give it are our basis functions. Same thing for our kinetic energy. Build kinetic. We only need to give it our basis functions. Then we need to nuclear attraction. It's going to be our matrix for nuclear electron nuclear attraction. Build nuclear attraction. And that we're going to have to give it our basis set. Let's give it our atomic numbers, our atomic coordinates, and then our basis functions. And then finally, we need to build our four-dimensional array for the electron-electron repulsion. And so we're going to say G, A, B, C, D, where A, B, C, and D are going to refer to the individual orbitals.